Hello, welcome to lecture 5 of the course. In the last lecture, we have started discussing atom field interaction where the atom is treated quantum mechanically and the light field is treated classically. We have learned about the so-called rotating wave approximation, which is one of the most important approximation in quantum optics. We have also seen that how going over to a rotating frame of reference enable us to simplify the coupled differential equations that govern the dynamics of the atom field interaction. So let us continue our discussion. In the last lecture, we obtained this coupled differential equation describing the dynamics of the two-level atom under the so-called rotating wave approximation when it is interacting with the classical laser field. Here these coupled equations basically shows how this probability amplitude evolves in time, and this capital omega is the so-called Rabi frequency and small omega is the frequency of the laser field and omega 0 is the resonance frequency of the atom. Then going over to the rotating frame of the laser field where we are making this transformation, and this transformation if we make, then we obtain this set of coupled differential equation describing the dynamics of the atom in the rotating frame of the laser field. And here as you can see, by this transformation when we make, we are now able to get rid of the explicit time dependence on the right hand side of the equation. So basically it amounts to when we go to the rotating frame of reference, it basically means that we are going from the old state vector to a new state vector, and this amount to, mathematically speaking, making a unitary transformation via this unitary operator u. And because both this state vector psi in the old coordinate system and psi tilde, that the state vector in the new coordinate system, has to obey the Schrodinger equation, and using some algebra, very straightforward algebra, it is possible to show that how the Hamiltonian, and by the way, because if this transformation is made, the Hamiltonian which is h in the old coordinate system is now is becoming h tilde in the new coordinate system, and this new Hamiltonian is related to the old Hamiltonian by this relation. And in the specific case under our consideration, that is where the atom is interacting with the laser field, this Hamiltonian is given by this particular expression. And you see, going from the old coordinate, old state vector psi to the new coordinate psi tilde is, as I said, making a unitary transformation. So let me explain a little bit more. So basically what we are doing, we are making the unitary operation on the state vector, old state vector kth psi, and your kth psi is Cz kz in the basis state kz and kte. So this is what we have, and this is going to turn it, because of this transformation we'll get Cz kz plus Ce e to the power I omega t e, and this guy we are terming it as Ce tilde. Okay, and as I already told, h is going to h tilde when we have made the transformation. And this unitary transformation, it is easy to see from this equation here that this transformation is nothing but u is equal to e to the power I omega t kate e bra e. So this is the unitary transformation, and in fact using this in the problem solving session I will explicitly get this particular Hamiltonian using this particular relation here that we have, as I have asked you to derive it. I still request you to please try to do it again, otherwise anyway I'm going to do it in the problem solving session. Now to sum up what we have originally this Hamiltonian, and this state vector, then making a unitary transformation. By the way, this Hamiltonian we are writing in the so-called rotating under the so-called RWA or rotating wave approximation, and then making a unitary transformation. We are going over to this Hamiltonian, and the state vector is becoming now psi tilde. So now let us solve this coupled set of differential equation that we have worked out by going over to the rotating frame of reference, and we are going to consider the case of resonant interaction, that is when delta is equal to 0. That means that when the laser field frequency matches exactly with the resonance frequency of the atom, then this coupled differential equation under this condition would become simply delta Cg delta T is equal to minus I capital omega by 2 Ce tilde. Let's say this is my equation number 1, and delta Ce tilde delta T is equal to minus I omega by 2 Cz. Let's say this is equation number 2. Now we can differentiate equation number 1 with respect to time and use equation number 2, and then we are going to get this second order differential equation delta 2 Cz delta T2 is equal to minus omega by 2 whole square Cz, or let me just write it in this form, delta 2 Cz delta T2 plus omega by 2 whole square Cz is equal to 0, and this is a well-known equation. And in fact, similarly you can get the equation for Ce tilde also. You can get delta 2 Ce tilde delta T2 plus omega by 2 whole square Ce tilde is equal to 0. Let's say this is my equation number 3 and this is equation number 4. Now the general solution of this equation number 3, we can write it because it's a simple harmonic equation and all of you are familiar with it. I can write it as its general solution would be A sine omega by 2 t plus B cos omega by 2t. This constants A and B can be found out from the initial conditions. If I consider this specific condition, say at time t is equal to 0, the atom is in the ground state. Say at time t is equal to 0, the atom is in the ground state. Then I can take this amplitude coefficient Cg at time t is equal to 0 is equal to 1, because you know Cg mod square gives the probability of finding the atom in the ground state. Now because it is in the ground state, this is equal to 1, and obviously the atom is not in the excited state, so at time t is equal to 0, Ce tilde is equal to 0, and using these initial conditions we can obtain, please try to show it yourself, it's very straightforward. You can show that Cgt is equal to cos omega by 2t and Ce tilde t is equal to minus I sine omega by 2t. Okay, so we have obtained the probability amplitudes for the atom when we have considered the atom to be in the ground state initially, and from here we can immediately write down the probabilities for the populations in the ground state and the excited state. Probability for the population in the ground state would be simply given by Cgt at any given time would be Cgt mod square, and that is going to be equal to cos square omega by 2t, which is nothing but 1/2 1 plus cos omega t, and then Pe, the probability of getting the atom in the excited state, is Ce tilde t mod square, and that is nothing but sine square omega by 2t, and which is equal to 1/2 1 minus cos capital omega t. We can represent this population graphically with respect to time. If we plot that, we will find this particular plot. Here the red curve represents the population of the ground state and the blue one represents the population of the excited state. And in the x-axis, we are plotting it with respect to the product of capital omega into time. As you can see from this plot, that at time t is equal to 0, the atom is in the ground state, and at time t is equal to pi by capital omega, or the product omega t is equal to when it is pi, the atom is in the excited state, because the excited state population is 1 now and the ground state population is 0. So, and after some time, that is when omega t is equal to 2 pi, the atom is going back again to the ground state and the excited state population is 0. And this way, as you can see, the population is oscillating between the ground state and the excited state, and this oscillation is happening at the Rabi frequency capital omega. This is the omega is the population oscillation frequency. And this particular phenomena where the population is oscillating back and forth between the ground state and the excited state, this phenomena is known as the so-called Rabi flopping. And this is a very important phenomena when I am going to come back to this particular phenomena later on, when I will discuss applications of quantum optics in the context of quantum computation later on, and we'll see how this particular phenomena can be utilized to manipulate quantum bits. Now, as you can see from this Rabi flopping phenomena, that the all eigenstate, our all eigenstates Kg and Ke are no longer the eigenstate of the new Hamiltonian, right? Kg and Ke are no longer eigenstates of this Hamiltonian H tilde, which is the Hamiltonian for the couple system. But still we can find out the new eigenstates of this Hamiltonian, and let us do that. Now, as we have seen that H tilde is equal to minus h cross delta, we are still working in the rotating frame of reference and under the RWA. So our Hamiltonian is this minus h cross delta kt bra e plus h cross omega by 2 sigma, which is basically the atomic lowering operator. Let me write it in this form, and this is nothing but my sigma, and then I have kt bra z, and this is my sigma dagger. This particular Hamiltonian I can write in the matrix form. So this would be h cross minus delta, and this coupling terms would go here, omega by 2 here, in the off diagonal terms it will sit there, and I am taking the ground state here. Now it is 0, the ground state energy anyway we are taking it to be 0. So this is my coupled Hamiltonian in the matrix form. And let me now solve this eigenvalue equation. So our eigenvalue equation, the Schrodinger equation is this. Schrodinger equation is this, and where, let me write it this in this form, delta psi t is equal to minus I by h cross s tilde, this is psi tilde, okay. And as you have seen that psi tilde is equal to cg kg Ce tilde Kate E, and this I can write in the matrix form. It would be represented by column vector. So here I am writing the excited state in the upper upper row, and ground state in the lower row. So this is the representation of the psi tilde, and in terms of this matrix form I can write down my equation in this way. It would be Ce tilde Cg is equal to minus I h cross will actually get cancelled out, and therefore I will have this particular expression this form. So this is what I'm going to have. Okay, this is my coupled equation, which already we are aware of. By the way, I am interested in finding out the eigenvalues of the Hamiltonian, and thereby I am going to find out the corresponding eigenstates. So the motive is to find out the new eigenstates. So let me once again go back to my Hamiltonian in the proper form. It is h cross minus delta omega by 2 omega by 2 0. You can easily find out the eigenvalue of these equations. So how to do that? Let me quickly show you. You just have to find out the characteristic equation. So the procedure, I'm just very briefly quickly letting you know. So this equation you have to solve, and let me leave it as a homework to you, as a exercise for you. You can easily show that eigenvalues would turn out to be lambda is equal to minus delta plus minus square root of delta square plus capital omega square divided by 2. And as you can see, there are two solutions, and these are the eigenvalues of the Hamiltonian. So they basically represents energy. So let me write down the energy term, which says higher one is E plus, and E plus represents lambda with this plus sign, and another eigenvalue would be E minus, that would be with minus sign. So first let me write down the plus one. E plus is equal to minus h cross. You should not forget about h cross, by the way. Okay, it would be here, you will have here h cross would be there. So h cross delta by 2 plus h cross by 2 delta square plus omega square. I can write it in a short notation as well. Let me write it as h cross delta by 2 plus h cross omega tilde by 2. I will soon write what is omega tilde, and you can easily make it out what is omega tilde. And E minus is minus h cross delta by 2 minus h cross by 2 square root of delta square plus omega square, which I can write in short notation as minus h cross delta by 2 minus h cross omega tilde by 2, where as you can see omega tilde is the short notation for capital omega square plus delta square. So these are my eigenvalues, and let me say this kth plus is the corresponding eigenstate for the eigenvalue E plus, and E minus corresponding to E minus, I have the eigenstate kth minus that corresponds to this eigenvalue E minus. So let me find out this kth plus and kth minus, but let me play a trick here. I can always express any state, as you know, any quantum state as a superposition of the basis vector. So if I can write this kth plus also in terms of the basis vector kg and ke, and let me write it in terms of kg and kt, and the coefficient has to be such that its mod square should be equal to 1. So let me take the coefficient for kg as sine theta, and associated with the kt is obviously going to be cos theta, right? So this represents the eigenstate, and I'm going to find out what is sine theta cos theta later on. And similarly for the other one, kth minus, it has to be such that, you know, let me first write it, and there is a reason why it has to be of this form. It would be cos theta kg minus sine theta kt. Okay, this is the minus kth minus, which corresponds to the energy eigenvalue E minus, and this kth plus corresponds to the energy eigenvalue E plus. Now let me tell you why I am writing kth minus in this particular form. Once I write kth plus in this particular form, Kate minus has to be of this form because Kate plus and Kate minus are the eigenstates of the new Hamiltonian, and because they are the eigenstates or the basis vector, they have to be orthogonal to each other, and this particular relation has to be obeyed. And if you actually check it, then you will get it, provided you are choosing Kate plus and Kate minus in this particular form. And this angle theta has a name, and it is called Stuckelberg. It is called Stuckelberg angle. It is called Stuckelberg angle, and it is defined by this expression: tan 2 theta is equal to minus capital omega by delta. Let me actually show you how this expression, how this is actually coming. Okay, so to do that, let me first write down the eigenvalue equation corresponding to the basis state. Now new basis state, say Kate plus, that is equal to E plus Kate plus. This is my eigenvalue equation. Let me write down my Hamiltonian in the matrix form. So it is H cross minus delta omega by 2 0, and Kate plus I can write, now you see Kate plus, once again you see I am writing the excited state in the upper row, so therefore here I am going to write here cos theta, and in the lower row I am going to write sin theta, and I have E plus and Kate plus. Again here I am having cos theta sin theta, and let me open it up. Just one equation is sufficient to get my theta. So to do that, let me write minus h cross delta cos theta plus h cross omega by 2 sin theta, that is equal to E plus cos theta. E plus cos theta, and already I know the expression of E plus cos E plus, so let me write it: minus s cross delta cos theta plus s cross omega by 2 sin theta, and E plus, which we have already worked out. Yes, we have this expression here, so let me write down the full expression. So this is going to give me minus s cross delta by 2 plus h cross omega tilde by 2 cos theta. Okay, and it's very easy affair to manipulate it, and if I from here I can immediately write tan theta. If I shuffle the terms, then you will find that tan theta would be equal to, it's very trivial to show this, you will get delta plus capital omega tilde by capital omega. So this is how I can find my angle, but let me show you how this is obtained. To get it, just you know that tan 2 theta is equal to 2 tan theta divided by 1 minus tan square theta. So you just have to utilize this identity, and tan theta is already you are having, just put it there, and if you do the simple mathematics, very straightforward, ultimately you are going to get it as capital omega by delta. So that's how this angle theta is defined, and we are now obtaining this particular expression. Now this angle theta is constrained between 0 and pi by 2. Please think about it, why it is so. Maybe I will explain it in the problem solving session. Now these are my new eigenstate Kate plus and Kate minus. These eigenstates are known as the dress state. These are called the dress states of the atom. Now let us analyze these eigenvalue expressions. E plus minus is equal to minus s cross delta by 2 plus minus s cross omega square plus delta square under root divided by 2, and it is quite useful to analyze these expressions graphically. Now before I analyze it, let me first consider the simple case where there is no coupling. Let us consider that situation when there is no coupling. If there is no coupling, that means my capital omega is equal to 0, and this would mean that E plus minus is equal to minus S cross delta by 2 plus minus S cross delta by 2. So this will give me E plus as 0 and E minus I will get it as minus S cross delta. So E plus refers to the ground state energy, because already we have taken the ground state energy to be 0, as you can remember, and now the excited state has energy minus S cross delta. So if I plot it when there is no coupling, if I plot E versus delta, let us say in the y-axis I have energy, and x-axis I have this detuning parameter, then the ground state represents energy 0, so ground state is going to be represented by this when there is no coupling. This refers to the ground state, that is Ez is equal to 0, and the other one E minus is minus S cross delta, so it says a negative slope, so it would be of this type. It is going to go like this, right? So this is my excited energy, so that is minus S cross delta. Now as you see, these energy curves cross when delta is equal to 0. They cross at delta is equal to 0. Okay, this is an important result. Now if I consider the other case, general case, when there is coupling, that means when omega is equal to non-zero, when capital omega is non-zero, that means there is coupling, then my E plus is equal to minus S cross delta by 2 plus S cross omega tilde by 2, and E minus is equal to minus S cross delta by 2 minus S cross capital omega tilde by 2. And if I once again plot E versus delta, then I am going to get this plot. So I have here in the y-axis energy and here the detuning parameter delta. Now when there was no coupling, as you have seen, it is basically these two energy curves crossed at delta is equal to 0. But when now there is coupling, now you will see that these two curves no longer coincide. So E plus is going to be represented by this plot. Let me draw it properly. So this would be go like this. This is your E plus, and the other one is E minus, and E minus would go like this. Okay, so these hyperbolic plots you are going to get, and here at delta is equal to 0, this gap is nothing but this gap is going to be capital omega, and this red one represents E minus. So when there is coupling, so you see that these two energy curves are no longer crossing, and this is known as avoided crossing, a very generic phenomena when there is coupling. When there is coupling, we are having avoided crossing, and coupling is happening because the laser radiation or laser field is interacting with the atom, and this gives rise to the so-called avoided crossing, and it has lot of applications, and we are going to discuss one simple application called adiabatic basis. Say you have a two-level atom, and the atom is in the ground state initially, and you want to make it to go from the ground state to the excited state. To do that, generally what we know from our learning is that we just have to send a laser field, a classical laser radiation. If we make it incident on it, then from this result that we have discussed earlier, that when the atom is in the ground state initially, if I throw the laser pulse for a time t is equal to pi by omega, or this product capital omega t is equal to pi, then as you can see from this plot that the atom is going from the ground state to the excited state. Okay, and when omega t is equal to pi, this kind of pulse, laser pulse, is known as the pi pulse. But the problem with this technique is that we have to focus the laser so tightly that it has to exactly equal to the resonance frequency of the atom. That means omega is equal to omega 0, because as you can recall that we are doing the analysis for the resonant case, and to get delta is equal to 0, we need to have a very stable laser, and which causes practical problem, and in many times it is not possible to focus the laser so tightly because of the stability issue. And to get rid of this trouble, what we can do is that we can apply a trick, and the trick is that you change this detuning parameter delta, where delta is defined as omega minus omega 0, that you need not have to have exactly delta is equal to 0. Rather, what you do, you change the detuning parameter delta below the resonance frequency delta. If you change very slowly, or the laser frequency if you very slowly and approaches the resonance frequency of the omega 0 and cross it further slowly, then it is possible to make the transition from the ground state to the excited state, and this phenomena is known as the adiabatic passage. Let me explain how it is done and what is the physics behind it. To do that, just recall this again, these particular states, the so-called rest states. Because the laser field is now interacting with the atom, we are having these rest states. And let's say we start in the rest state Kate minus, which is a superposition of the ground state and the excited state, and we are far below the resonance frequency. That means delta is equal to 0 if we are having this side. So let's say we are starting here, and that means if delta is much less than minus omega, where capital omega is the Rabi frequency, or minus delta is much greater than capital omega, which is the Rabi frequency, then from this expression, as you can see, tan 2 theta, that's how this Stackelberg angle theta was defined, is equal to minus capital omega by delta. And because of this condition, as you can see, that the phase angle theta is equal to 0, and if you put theta is equal to 0 in this particular expression for the Kate minus, cos theta is going to be equal to 1, cos theta is 0. So initially the rest state Kate minus is equal to Kate z. So we are in the ground state, right? So here we are in the ground state, we are starting from here. Now let us sweep the laser frequency, that means change the detuning parameter delta very slowly over delta is equal to 0. If we go on and cross delta is equal to 0 very slowly by changing the laser frequency, then when delta is much greater than capital omega, then again from this expression tan 2 theta is equal to minus capital omega by delta, you can see that the phase angle is going to become theta is equal to pi by 2, and if you put theta is equal to pi by 2 in this expression for the Kate minus, you will find that your this rest state Kate minus is equal to Kate E. That means the atom is now going over to the excited state. Interestingly, you should see that you are still remaining in the rest state Kate minus, but you are going from the ground state to the excited state. Okay, and while you are doing it, this sweeping of the laser frequency has to be slow enough, and then you will be able to go from the ground state to the excited state. Now how much slow is to basically decide it, there is a problem called, this problem is known as the, to decide that how much slow is, this is called the Landau-Zener crossing problem. This is not we are going to discuss here in this course, but the main result is that if your Rabi frequency is much higher compared to the sweeping speed, or that is if omega square is much greater than the sweeping rate of the detuning parameter, then the population adiabatically follows from the rest state and makes the transition. That means you can go from the ground state to the excited state, or vice versa. If you are in the excited state, you can go to the ground state, or if you are in the ground state, you can go to the excited state. So this is a very important phenomena, and this is used in many experiments. Let me stop here for today. In the next lecture, we are going to do some problems based on lecture 4 and lecture 5. That is in the problem solving session number 2. and this will be followed by a discussion of various representation of the quantum state of a system in lecture number 6, which is going to be very useful for later part of the course. So see you in the next lecture. Thank you.